So good afternoon all. So today we will say some concept on thermodynamic measures and then we will solve the problems. So I think all of you have gone through the week 8 lectures which were available on which are available on the SWIM portals. So for starting from the ideal gas mixture, so if n moles of ideal gas mixture occupied a total volume V2 at a mixture temperature T, the mixture pressure P is given by P is equal to nRT. And if Ni moles of species are in the mixture occupy the same volume Vt alone at the same temperature P, the pressure Pi is given by for the species, right? Please make your mind someone. Okay, so Pi is equal to Ni RT divided by Vt totals. Using two equations, so Pi divided by P equal to Ni by N equal to the mole fraction. So this is a Pi equal to YIP. So this is partial pressure, this is total pressures, right? So Gibbs theorem is state that a partial molar property other than the volume of species in the ideal gas mixture is equal to the corresponding molar property of the species as a pure ideal gas at the mixture temperature and pressure equal to the partial pressure in the mixtures. Last session, someone had some doubt on why. Oh, here is the partial pressures. So the partial molar volume species I in ideal gas mixture is given by Vig is equal to dNVig dNi at constant temperature, pressure, and molar composition. Then put V is equal to nRT by P. Then you will get this RT by P dNy dNi at constant Nj means different composition except I. So with is equal to RT by P. So dNi plus summation of starting from the G Nj divided by dNi is equal to RT by P equal to Vij. So Vij equal to Vig, right? Only for the volume, right? Now for others means at the same temperatures and pressures. But other properties is the pressure equal to its partial pressures. That's the Gibbs theorem. Right. Now partial molar properties of the ideal gas mixture. So Vig is equal to Vig equal to RT by P. For SIG, so Gibbs theorem states that MIIG, this is partials at T temperature and pressure equal to MIIG equal to T and Pi, right? So this is the Gibbs theorems. Right. So for other property, the pressure equal to the partial pressures. M I I G T P I. PI indicate the partial pressures. So for enthalpy, was H I G bar P H I G T P I. But enthalpy is independent of pressures. So P and P, right? So partial molar enthalpy is equal to the molar property of pure species, right? Similarly, for the internal energy, means partial molar internal energy equal to the internal energy of the species, pure species, right? Similarly, for the enthalpy, so we know the equation for enthalpy. Calculate Ts is equal to Cp dt by T minus R dP by P, right? So at a constant temperature, so Ts is equal to R dP by P, right? So for ideal conditions, so you can write down this Ig is equal to minus R d ln P, right? At a constant temperature. So now integrate uh, uh, this equation from Pi to integrate from Pi to P, right? Yes, Ig Pp minus yes Ig P small, right, equal to minus R ln P by Pi, right? So here you can write down the partial pressure equal to the mole fraction into the total pressures, right? So uh, total pressure get cancels, you will get 1 by Yi. Si Ig P is small Ig P minus R ln Yi, right? All of you getting or not? Yes, right. Here is 1 minute. Now here these terms take here. So here 1 minute. PPI here it should be positive. 1 minute. Okay, okay. When here you get 1 by I ln, right? So if you convert ln, so here is the negative signs, right? When you write down here, so negative signs will get cancels, right? So here positive, getting or not? Now you can write down for this is the Gibbs theorems, m means partial molar properties at a temperature pressure equal to the uh, molar properties of pure species at temperature and partial pressures. So here you can write down S I I G T P, right? The partial is equal to S I I G T P R ln Y, right? So after that you can write down, right? Yeah. Now we get partial molar of enthalpy. So we know the equations, G H minus Ts, right? So you can write down Ig, Ig, and Ig. Put the partial. Now put the Hig value here. So you will get this one. So partial Gibbs properties. Partial molar Gibbs properties. All of you got clear, I think. Clear or not? Okay. So here write down in summation term from summability equations. So H I is equal to summation starting from I yi H I Ig with bar. Similarly for the Sig and for Gibbs free energy. Now coming to the property change of mixing. So we know the summability equations. Summation xi mi. So here delta m. So delta denoted by property change of the mixings. So delta m is equal to mi minus summation xi mi, right? Now put the all the properties here, like here internal energy. So delta u equal to u minus summation of, you can yi. So this is for the liquid. Xi indicate the here yi ui. So you will here is a derived. So uig at Tp minus summation of yi ui at temperature and pressures. So you can write down these terms in, so summation of yi ui ig with bar temperature pressure minus ui ig at temperature pressures. So here summation ui uig Tp from the Gibbs theorem is a partial pressure minus summation of yi uig at Tp. But internal energy it is independent of the pressures. It's a total pressures, so it get cancelled. So total internal energy change of mixing is a 0, right? Now change of mixing for the enthalpy. So here enthalpy also independent of the pressure. So enthalpy change of mixing for the ideal gas is also 0, right? Now for the entropy change of mixings, so we derive dig is equal to minus rd lnp, not derived, we get from uh, the properties from the pure fluids. Cp dt by t, Cp by p, right? So at a constant simpler, these terms get cancelled and get, so this one. Now integrate from pi to p, you will get this Si g at Tp minus Si g Tpi or ln p by pi. Okay, right. Now Sig Tpi, so it give these terms give. So Sig Tp minus r ln. So from Gibbs theorems, you get Sig means this is a partial properties of enthalpy or entropy at temperature pressure equal to the Sig Tp minus r ln y. So write down in summability relations, summation via Sig T, okay, P P equal to summation via Sig Tp minus r summation via ln y. So SIGTP is summation of yi SIIG temperature pressure minus r summation yi ln y. You will get this. This is the delta S mix Ig. This is the entropy change of mixing. Similarly, for you know the relation G is equal to H minus Ts. So put the value SIG and SIG. You will get this. Delta G mix Ig equal to RT summation yi ln. Now we can write down the uh, mu means the chemical potential at ideal condition equal to G means partials Gibbs energy at ideal condition. So these are the properties with change of mixing. This is the same one. Now based on the partial model properties and change of mixing, we will solve some problems. So starting question number 1. For ideal gas, the enthalpy change of mixing is, yes, right. For is enthalpy and volume also 0, right? And internal energy 0. Q mix to delta V mix delta H mix is 0. For ideal gases, the entropy change of mixing is, right. For ideal gases, the Gibbs energy change of mixing. The question 5, the for ideal gases, the entropy change of mixing depend on. Here is the as per the X mix. Right. Because the equations are summations yi ln yi. Right. It depend only the composition of the mixtures. And question 6, the for ideal gases, the Gibbs energy change of mixing depend on. Right. It is a numerical based on the change of mixing property. So a binary mixture is prepared by mixing 100 moles of each of the two ideal gases at 25 degrees Celsius and 1 atm. The entropy change of mixing. Option are given. Use the formula of entropy change of mixing and calculate. Here as for the binary delta X mix, right, are summation yi ln yi. But here as 2 means binary, yes, and each 100 moles are y1 ln y plus y2 ln y2, right. So it's a mole fraction 0.5, just 100 hundreds, right, divided by, so here 1 by 2, right. I'll cut clear or not? Here as for the binary mixtures, right? The answer is C. Now question net, ternary mixture is prepared by mixing 100 moles of each, sorry, each of three ideal gases at 25 degrees Celsius and 1 atm. The Gibbs energy change of mixing. The concept is same. I'll have to write. Sorry. Okay, okay. 1 minute. Also calculate. Right. Delta G mix equal to RT summation yi ln y, right. So write down for the three component, then you will get value minus 2721.86 joule per mole. Right. Question 9. 0.75 meter cube of CO2 and 0.25 meter cube of N2, each at 1 bar and 25 degrees Celsius, are blended to form a gas mixture at the same condition. Right. If CO2 and N2 are having a like ideal gases at these conditions, the change of entropy is equal to. There we have to calculate change in entropy. Negative, there is no possibility for the negative. Please recheck. Yes, 0. Okay, 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 okay. Yeah, right. It should be negative. Right. Yeah, yeah, right, right. You are right one. Mm. Delta is okay. One by y one. Okay, okay, right. It is a delta yes mix equal to minus r summation via lni. So we can write down here summation yi, right? Mm. Now use this expression, so you will get positive 0.5623 r. Yeah, all right, all right. Now coming to the fugacity. So can someone tell why we need to study the fugacity? Not means fugacity is used for the to represent the behavior of the real gases, right? So it's derived from the Latin word fleetness, means scheme tendency. It widely used for study the phase and chemical reaction equilibria involving gases at the high pressures. Now the fugacity is mainly applied to the mixtures. So here, so at reversible change occurring in isothermal conditions. So you know the relation dg equal to vdp minus hgt. So now reversible change occur at isothermal conditions. So temperature so this get cancelled. So dg equal to vdp, right? If I integrate, sorry, 1 minute. For ideal condition, V is equal to RT by P, right? So put here RT. So we can write down this RT D ln P, right? So if you integrate, so you will get this term, right? So this is a constant term like C. It's depend on only temperature and nature of the gas. But this equation is not applicable for the other gases like real gases. So we have to represent the influence of pressure on the Gibbs free energy of real gases by the similar relations. Then, so we have to, this is the two true pressures. So we have to replace by the effective pressures, which called the fugacity. So here mu ig means this is same g mu ig is equal to RT, sorry, ji is equal to RT ln A pi plus constant term. This equation for the ideal conditions, and this is for the any state, right? A unit of fugacity equal the unit of the pressures, right? Now suppose this is equation 1, equation 2. So now gi minus gig equal to RT ln A pi by P, right? So we know the residual properties formula, actual minus MIG, right? So this get a GI with superscript I, R indicate the residual property equal to RT ln phi. So here fugacity divided by pressure equal to the fugacity coefficient, right? Getting or not? Means so under means represent the behavior of the real gases. Just like here for ideal gas pressure use. So here for the real gases we have to replace by effective pressures. That's called the fugacity. So here for a pure species, coexisting liquid and vapor phase are in equilibrium when they have same temperature and pressure and fugacity. Therefore the Fi with superscript L equal to the FIV equal to Fi saturation equal. Similarly, fugacity coefficient also similar for uh, similar at equilibrium condition. So you can write down uh, for species are in the mixture of the real gases or in a solution liquid, mu I equal to RT ln Fi with bar plus is constant. You can write down in simple C. So here Fi with bar is the fugacity of species I in a solution. So Gi with bar equal to RT ln phi I with bar. This is the fugacity coefficient. So fugacity coefficient equal to the Fi with bar equal to partial pressures, right? G bar. So you can write down for the partial molar properties. So here uses a bar, right? So here is a not used for this is for the residual properties, just like G I R equal to RT ln pi. Suppose for, you have to use for the partial molar property, so you can take a bar equal to RT ln, right? Right. This is for the means like single component. This is for the means solutions. The solution. Right. So I with bar equal to the A pi with partial pressures here. For the mixtures, you cannot write down the total pressures. Here is the total pressure for the single component. But for the in a mixtures, you write down phi I with the bar equal to A pi bar equal to partial pressure, right? So A pi bar equal to mole fraction into total pressure, right? And for ideal conditions, so fugacity coefficient equal to 1, right? Uh, when the real gases at uh, pressure tend to 0, this is the limit conditions, it tends to 0, so it's behave like the ideal gas, right? So A by P equal to 0, sorry, 1 at P tends to the 0. So fugacity coefficient is the 1. So at that conditions, G I with superscript R with bar is a 0. So this indicate that therefore Fig equal to Yi into P, right? So this indicate that the fugacity of species I in an ideal gas mixture is equal to the partial pressure, right? All of you got clear or not? Now ideal solution. So so this is this equation GID. Here ID denote the ideal solution property plus RT ln xi. This is for the ideal solution, means mostly the liquid solution, and for gas mixtures GIIG equal to GI plus RT ln yi. So here yi denote for the gases mixtures, and xi denote for the liquid mixture. Right. So VI ID with bar equal to the VI. This is for the ideal solution. HID with the bar equal to the HI. Similarly for GID, summation xi gi plus RT summation xi ln. This is a simple similar to the gas mixture. So here just replace yi by xi, right? Ideal solution means liquid solution, liquid mixtures. Uh, Next is the Lewis-Randall rules. So here, if I means ideal conditions means ideal solutions with the bar equal to the xi fi. Okay. So here fig at means gas mixtures. So fi at ideal conditions with bar equal to the yi into total pressures. So here are ideal solutions fi with bar at ideal solution equal to xi fi. Right. This is the Lewis-Randall rule. It is applicable to each of species in ideal solution at all condition of temperature, pressure, and composition. Right. So you be dividing partial pressures Fi id equal to the xi pi p is total pressure equal to the xi fi system xi pi, so xi get cancelled, so fi p. So fi with bar at ideal solution equal to the fi. So fugacity coefficient of pure species are in the ideal solution equal to the fugacity coefficient of a pure species are in the same physical state as the solution at the same temperature and pressure, right? Clear or not? So based on the fugacity coefficient and ideal solution, we will see some problems. So question 10, the fugacity of species I in an ideal gas mixture is equal to, option are mixture of total pressures, its partial pressures, 1 and its mole fraction. No, here is asked for the ideal gas mixture. It's a part. Yes, right. And question 11, the fugacity coefficient of species are in a solution. Fi, right. The question tell, as a pressure approach to zero, the ratio of fugacity to pressures for the gas approach. 1 minute. But this is like the limiting conditions. This is F for the real gas, P for the ideal gas. So when pressure tends to zero, that means at a low pressure, so real gases behave like the ideal gas, right? So F by P I think it tends to the 1. Am I right? Like no, no. But this is a gate question. This is based on the concepts. If you put like this pressure, so this is like limiting conditions, right? Ruk, 1 minute. F by P, right? Uh, this represent for the real gases. This for the ideal gas. So there are some means limiting conditions for the real gases. Like pressure tends to the zero. So it's behave like the ideal gases. Getting or not? So it's like to P by P. Right. Now question number 13. The statement given here. The minimum work required to separate a binary gas mixture at a temperature T naught plus pressure P naught is, here is the expression given. Here Y1 and Y2 are the mole fraction. F1 and F2 are the fugacity of pure species. And T naught and P naught, and F1 and F2 are fugacity species in the mixtures. Okay, here is a mixture, right? And T naught, P naught, and Y1. If the mixture is ideal, then W is mm, mm, no. Here we have to use the Lewis-Randall rules. This one, right? Fi with bar equal to the xi Fi, right? So Fi bar equal to, like here y, I can write down y, the Fi 1, right? So Fi bar divided by Fi equal to the y, right? So consider here y1 and y2, right? Based on the Lewis-Randall rule. So W is equal to minus R y1 ln y1 plus y2 ln y2, right? So here as far to separate the binary mixtures, right? So work is needed to be the needed to separate the mixture. So W should be positive. So these terms will be negative. Then we will get W is positive. Separate the gas mixture. The option is B, right? Now question 14. A binary system at constant pressure with species 1 and 2 is described by two suffix Margulis equation. GE is denoted by the excess property divided by RT equal to 3x1 to x2, where G is the molar excess gives free energy and R is a gas constant. T temperature, x1 a mole fraction of species 1 and 2 respectively. At a temperature T, G1 divided by RT equal to 1 and G2 divided by R2. Right. 2, where G1 and G2 are the molar gives free energy of pure species 1 and 2 respectively. At the same temperature, G represents the molar gives free energy of the mixture or a binary mixture at 40 mole percent of species 1. The value of G by RT is. Here we have to calculate G by RT. Here is the excess property mentioned. So excess properties GE actual and G ID ideal solutions, right? Excess property for the used for the liquid, and residual property mostly used for the gas mixtures. So actual and ideal, so ideal for the liquid. So G equal to G ID plus G, right? So here G with the superscript E by RT, G here given is for the GID. So G is equal to, so we can write down these terms, summation EXI GI with bar ID, right? Now we know for the ideal gas mixtures, for gas mixtures at ideal GI bar to GIIG plus RT ln YI. And similarly for the any sorry, for ideal solutions, GIID with bar equal to GI plus RT ln XI, right? So put down these terms in these equations. G is equal to summation XI GI plus RT ln XI. Here is the x1 given 0.4, right? Plus GE, right? Now here is the two pieces. Now divide by these terms by RT. Right. So x1 G1 by RT plus x2 G2 by RT. Here G1 and divided by RT given here given, right? X1 RT get cancels. So ln x1 plus x2 ln x2, right? Here is the two component here plus G T R T, right? We have to calculate this term. X1 given 0.4, so x2 is a 0.6. Understood or not? I have to put the value with G by RT. Mm, not you can we can use for also ideal solution like liquid also. So it used for the mixtures. or it may be gaseous or liquid. What is the value of G by RT? If you calculate, tell. Point 6, 1.65. Getting or not? G by RT equal to 1.65. Right. Now question number 15. Uh, Please make your mic mute. Okay. The vapor pressure of pure substance at temperature T is 30 bar. The actual and ideal gas value of G by RT for saturated vapor at this temperature T and 30 bar are 7 and 7.7 respectively. Here G is the molar Gibbs free energy and R is the universal gas constant. The fugacity of the saturated liquid at this condition rounded to the 1 decimal place is per unit. So here is a 30 bar given. Right. So the actual and ideal gas value of G by RT for the saturated vapor at this temperature and pressure are 7 and 7.57 respectively. So you have to calculate the fugacity for the saturated liquid at these conditions. So we know dg equal to RT T ln F, right? So T ln F is equal to dg by RT, right? Now integrate this from pressure P to F, P to F. Ig, right, dg by RT. 60, 60. Now please recheck. So when integrate, so you let ln F by P, right? So G by RT minus G Ig by, right, RT. So here this is for actual of G by RT here given 7, and at ideal condition G by RT given 7.7. So and P given initially better, right? Put, right. So you get AP is equal to 14 point. Now question number 16. At high temperature and pressure, N2 obey the equation of state P into V minus B equal to RT. Calculate the fugacity of N2 at 1000 degrees Celsius and 1000 atm the pressures if B is equal to 39.1 centimeter cube per mole. Calculate the fugacity coefficient. So you have to calculate the fugacity and fugacity coefficients. This is the equation of state given. Please read the problem statement and tell some approach how to solve. Take a time. So we know the M1 relations for Gibbs energy Tg at ideal condition equal to RT T ln T, right? For ideal gas. For any and for any state Dg equal to RT T ln F, right? So Dg minus Dg Ig equal to the RT T ln F by P, right? This is residual property, right? P R equal to RT T ln I, right? Take equation 1, equation 3. Now from the fundamental property relation Eg equal to VdP minus SdT. So at a constant temperature, it get cancels. We can write down for the residuals, right? So volume for at ideal condition V is equal to RT by P, right? At ideal conditions, and for any state, how can how can we write down for volume for the ideal? ideal conditions or any conditions. Can someone tell? Right. Z RT by P. So Z here Z is a compressibility factor. It's help to represent the behavior of the real gas. Right. So now here are right. So similarly for DG DGR is equal to P TP S P IG TP. Right. So put down this value here. So Z minus 1 RT TP by P. Right. Equation 3 and equation 4. Right. So now from equation 3 and 4, we can write down ln I and integrate from 0 to P Z minus 1 TP by P. Right. Here given equation of state P into V minus B is equal to RT. So now based on that you have to put the value of Z, make it this equation in Z form and integrate and calculate the fugacity coefficient and fugacity. So PV minus PB to RT, right? So PV equal to RT plus PB, right? If you divide by this equation by RT, right? The compressibility factor, right? 1 plus PB RT. Now put this value Z in this equation and integrate and calculate the phi. All of you getting or not? Sorry. Hi. Yeah, right. Now put this value here in this equation, like 4, 5. ln phi is equal to 0 to here 1000. So 1 will get cancels, so pb by rt. What? Yeah, you have to change the unit of the b. pp will get cancelled. pp will get cancelled. ln phi 0 to 1000 p pp. Make it into a meter cube per mole. 39.1 into 10 to the power minus 6 meter cube. Now R value 8.314 joule per mole Kelvin. Now here convert degree Celsius to Kelvin. So ln phi equal to 0.373. All of you get this value ln phi.
Yes.
Yeah, 1 pi high, right. Now man fugacity. Right. Uh, Unit of fugacity. Okay. I is equal to 1.453 and f is equal to 101453. Right. So I cover all the question based on the concepts like uh, ideal gas mixtures, then change of mixing properties, then fugacity and fugacity coefficient, ideal solution, and Lewis random. If you have done, if you have any doubt, please ask. Yes. As the pressure approaches to zero, the ratio of fugacity pressures F by P for the gas approach. So if you can look like a simple, so it's a infinity. But if you put means limiting conditions, so it's will be unity. One minute. So ideal gases applicable at low pressures and high temperature. Am I right? So ideal gas applicable only at low pressure, but at other conditions, ideal gas is not applicable for the real gases. Means at a deep real means other gases which uh, come with sustain at high pressures. So uh, any real gases when we put the limit condition means pressure tends to zero, so it behave like the ideal gases means all means real gases behave like the ideal gases. Uh, yes. So here is a F for use for the real gases. So if you put a limit P tends to the zero, it's behave like the pressure of ideal gas, right? So P, that's the comes unity. That's the concept here. Okay. 1 minute. If you put a limit temperature tends to okay. 1 minute. T tends to infinity. High. Please repeat it. Yes. Ratio. So generally, this fugacity terms come from one relations dg v equal to vdp minus sdt. So at a constant temperature. So SDT get cancels terms. So based on I think here is a means there means 1 minute. Is a temperature role in this fugacity concepts? No, is a temperature any roles in this fugacity relay the fugacity concepts? Mm. Yeah. 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 1 minute. Temperature and pressures. Pressure infinity tends to zero. So what would be the answers? It should be, I think, no, no. You pay, you put it like t like t tends to the infinity. Sorry, am I right? I think you were saying something like if you put a limit like t tends to the infinity. So what would be the effect on this ratio? I need to check it. What would that effect on the temperature? Now I will tell you in the next sessions. So, sir, what do you think? If you put a limit t tends to the infinity, okay, yeah, right, right. But here is someone has some good intention or good questions. If you put a limit t tends to the infinity, so we have to once again we have to direct like 1 minute. But there will be the deeper different relation you will get. You will not get f by p. Will be 1 minute. Right. So here, 1 minute. So this terms, these terms dg is equal to vdp get at some certain condition like reversible change at isothermal conditions. So it will be the different for the other condition like isobaric. Right. Generally, here for the ideal gas is the total pressures. So the pressure must some influence of pressure on the Gibbs free energy of the real gases by the similar relationship. So they here we have to derive some similar relations just like this Pg is equal to Vdp. So we replace P by the effective pressures that called the fugacity of gas. So if you go for a certain condition like constant temperature, then you will get the fugacity concept, fugacity terms. Right. But I will check what will the effect if you t tends to the infinity this ratio. Okay. Uh, okay, okay, okay. So here I'm actually I'm also using to make some assignments. So that's all. But at one times only one user can use only. Okay. Okay, here I shared ID and password. So for to make a assignment, I will use I am a subscription, I am a subscriber. That's why that's the problem. Yeah. All the questions from the I think 1990 to 2022, and all the solution given here. Okay, so thank you all. We will meet on next Saturday and next chapters.